Okay, so this statement here says that the dot product can be expressed as a matrix product. But you have to have a vertical matrix here and a horizontal matrix here to get a 1-by-1 result. And since we usually don't express matrix vectors as horizontal matrices, or I don't know how I can say usually, but I'll say usually we don't express vectors as horizontal matrices, but rather vertical. So if it was a vertical, then you couldn't do this. So we think of A as being vertical, but then we take the transpose to make it horizontal. But of course that's, again, assuming that A was initially expressed as a vertical matrix, which isn't always the case. Okay, she says, this is useful, matrix multiplication is defined in a way so that, roughly speaking, working with vector quantities or quantities involving several variables can be made to look as much as possible like working with a single variable. So let's see where that might happen. So a linear function in a single variable is it's a linear function, is a function of the form f of x equals ax. Now sometimes we'll say f of x equals ax plus b is linear, but that's not what they're calling linear here. Like, when you write the equation of a line, y equals ax plus b, sometimes we'll call that linear, but that's might be better called a linear equation. So anyway, a linear function here means something like this without the b. So now she says a natural generalization to higher dimensions, or anyway, something called a linear mapping, is a function from Rn to Rm. Now I don't think we've talked about functions like this yet. A function from Rn to Rm. So you can ask, this is bold, but this is also bold. So when this is bold, it means that the output is not one variable. So it's not just like a single y. Of course, here we're saying that the output is not just a single y. We're saying it's in Rm. Then in that case, we write this as a bold name. And then also, as we just said, the input is also bold, which means that the input is also a vector. So the output is a vector in Rm, and the input is a vector from Rn. So what function is this going to be? So here's the definition of the function. So we take the x, and we multiply it by some by some matrix A, just like we multiplied this by some constant A, where A is a constant m by n matrix, and x is in Rn. So does this make sense? If I multiply this x from Rn by an m by n matrix, so we have this as A is an m by n, and x is in Rn. So does this work? So how many rows does x have? So remember, typically we're speaking of vectors as a vector as being vertical. So it has rows. It has n rows, right? And how many columns? It has one column. And this is m by n, so this matches this, so that's good, so that's okay. And then the result is going to be an m by 1 matrix, so that means it's going to be, again, a vertical matrix with m rows and one column, so this is going to be in Rm. So it does work. So when you multiply by this size matrix, multiply x by that, you're taking something from Rn, that is x, and you get out something which is in Rm, which is what we said we wanted. Again, we write capital F bold to indicate that the output is also a vector. It's an m dimensional vector. So we have A, this is A, this is A, it's got m rows and n columns. And we have X, which has n rows, and same number of, this has the same number of rows as this has columns, and one column. Okay, so we were trying to talk about linear mappings, and they're suggesting somehow that doing this is a linear mapping. So for something to be called a linear mapping, it needs to satisfy two properties. It needs to satisfy this property and this property. So does this function satisfy those properties? So what are the two properties? That if you take f of x plus y, you can break that up into f of x plus f of y. And if you take f of k times x, you can rewrite that as k times f of a. So this is not true for every function. For example, if f of x equals x squared, this won't work. If you take f of x plus y, you get x plus y squared. That's not equal to x squared plus y squared. So that doesn't work. But does this work? So this is, when you do f of a plus b, x plus y, it's a times x plus y. But that's the same thing as a times x plus a times y. So that works. And this will also work. If you do f of kx, that's kax, and this is also kax. So this function is what's called a linear mapping. You might want to look up this, look up a video on this on the internet just to make sure you understand. But you should see that this doesn't work, but this will work. So this kind of function is linear. It satisfies these two conditions or properties, okay? Whereas this is not linear. Okay, so now we want to think about our matrix multiplication function. And we want to ask, is it linear? So this is what we mean. If we take f of x plus y, is that the same as f of x plus f of y? And also the constant multiplier property. So what about this? So what is this equal to? This is equal to, first you take x plus y, you add them together, and then you multiply that by a. And here, first you take, here you take x, multiply it by a, take y, multiply it by a, and then add those two results together. And the question is, do you get the same thing? Okay, so she's not going into that in too much detail here, so I guess it's left up to you to verify that this is true. So again, what you have to do is verify that if you take two vectors, both of them have to be in Rm, and you add them, and then multiply that by the m by n matrix A. Okay, that's the left-hand side. And then on the right-hand side, you take the first matrix and multiply it by A. And you take the second matrix and multiply, the second vector, I don't know if I said that right, the first vector and multiply it by A, and the second vector and multiply it by A, and then add those two together. Do you get the same thing? So you should check, I don't want to write it out, so you should check that this works. And also, if you take a vector, multiply it by a constant, and then apply f to it, is that the same thing as first applying f to it and then multiplying by the constant. Remember, applying f means multiplying by this matrix. They say these properties, of course, are also satisfied by this, which we did show that, I think, or we explained it. Perhaps more important, however, is the fact that linear mappings behave nicely with respect to composition. So they're talking about, we're talking about linear mappings, and first she said there's a kind of a nice way of writing a linear mapping as just AX, just like this is a, it looks like this. She wanted to say that vector equations sort of look like regular equations. And now she's also saying that linear mappings in this generalized form from Rn to Rm behave nicely with respect to function composition. So you should know what function composition is. So what about in this kind of, with these kinds of functions? So suppose we have this f like this, and then we also have another function g. Now g goes from Rm to Rp, so that's different than f, which is going from n to m. So is there anything similar? Well, this m and this m are similar. So why is it why does it look like this? Well, first of all, we're going to talk about g circle f. So that means we're putting f into g. You should know that notation. So that's g of f. G of f. So first we're doing f. So in other words, first we're taking things from Rn and mapping them into Rm. So we're from out of f we're getting Rm. And then g goes from Rm to Rp. So this is possible to think about this because what we get out of f is something in Rm, and that's what g needs. So g will take that to Rp. So you can see that when we do the composition, we're going to start with f, so we're going to start with Rn. That's going to get mapped into something which is then going to get picked up by g and mapped into Rp. So the composition is going to go from n to p. So it goes from n to p, from Rn to Rp. So g circle f, which is g of f of x. Now f, we said, is ax. So we have ax. Now, oh, we forgot to say what g is. G is another linear function, bx. So it takes its element and multiplies it by some matrix b. Now b has to be the right size, and so on, but let's just assume that b is the correct size. So we first do f, which means we're multiplying by ax, and then to do b, we just multiply this result by b. And these dimensions should work. For example, a was, we already said, m by n. And what is b? B is going to be p by m. And so the inner dimensions, so this multiplication will work. The multiplication of b times a will work. And so what we're saying is you can do ax and then multiply that by b, or you can multiply b times a and then multiply by x. And that comes from these properties, this particular property of matrix multiplication, that it's associative. So what we have is we see that the composition of two linear mappings, both g and f were linear mappings because they were both multiplications by a matrix, which we just above showed is the will be a linear mapping. And now we have that the composition of linear mappings is itself a linear mapping. And we see that here because G circle F of X, this is the composition, is just a matrix multiplication of X. This is a matrix, BA is itself a matrix, times X. So that says that if we start with two linear mappings and we take their composition, the result will also be linear. That means the result will also have this kind of property and this kind of property. So that's a very important and useful result. Okay, so now we're going to go back to when we wrote the equation for a plane, and we're going to see that we can write a nice equation for a plane in Rn. And that equation is going to look like this. Is going to be called a hyperplane, where x is in Rn. So let's see where that comes from. So remember before in chapter 1, section 2, I think it was, we had this equation for the vector parametric equation for a line. And we also saw that we could write that like this. And then we said that we could do a dot product like this. And this would represent all the points in a plane that were normal to n. This was the picture. So P0, P, any point P that satisfies the dot product equals 0 will give you a point in the plane. And P0, P, this vector here is given like this. And so if you expand this out with the normal vector being A, B, C like that, then you're writing n dot this equals 0, which can then be written like this. And we can generalize that to this if we have n dimensions instead of just 3, as in the last picture. Now, if we take A to be the vector A1, A2, we take this vector A to be A1, A2, up to AN, these here, and B to be B1, B2, and so on, and X to be the variable vector like P was before, as opposed to P0. This is like the P0, and this is the P. So we get, this is the P. Then we can write this equation up here like this. So we take x minus b, gives us each one of these terms, so on, and times the a's here. Now we can think of A as we can think of all of these as n cross 1 matrices. So these are all vectors, but we can think of them as matrices with n rows. And then we can rewrite this. We'll get the same thing if we write it this way, when we think of A as a vertical vector, or a vertical matrix, I guess. And then we take the transpose of it. So now it has n rows and 1 column, and these have 1 column and these have n 1 row and n columns. And so when we multiply that out, we get a basically one-dimensional vector, one-dimensional matrix, and we set it equal to 0. So we can rewrite the equation for a hyperplane. This is the equation for a hyperplane like this. And it runs through the point B and is normal to the vector A. and the elements of X are elements are, we should say, I'm sorry, X is an element of Rn. So this is a hyperplane in Rn. Okay, next we're going to do something that's a bit different. We're going to take an application of all of this to economics. So here the example is that we're thinking that we have n commodities, and each commodity has a price, and we'll call the price of the ith commodity P sub I. So if we purchase P items at a cost of, if we purchase X sub I items at the price P sub I, then the cost is this. So if this is the list of all the prices, and this is the number, corresponding number of items that we purchase for each item, for each commodity, then P dot X, which equals this, represents the total cost of the bundle that we purchase, the commodity bundle, the set of all the commodities that we purchase. They say, suppose we have an exchange economy, in other words, we can buy and sell stuff with some kind of limit on how much you can buy for each item. And this represents the limit on this is the amount, the limit on the amount of the first commodity that you can purchase, and this represents the limit on the amount of the nth commodity that you can purchase or that you can sell. So if you take the price vector dot this vector, that's the most that you have in terms of dollars. And so you can afford any commodity bundle which is less than this, and this is the cost of our commodity bundle, so this has to be less than this. They say you can rewrite this equation like this. Just factor out the p. In other words, you can afford any commodity bundle X in this set, the set where the set of all X, such that this is less than 0. The equation this equals 0 we recognize as a hyperplane, so we'll call it the budget hyperplane. And that represents basically the maximum that we can purchase or sell. And of course this hyperplane passes through, this is the point, so it passes through this point, or this vector, and the normal vector is P. Okay, next we'll do determinants. And this is just a short section on determinants. We already did 2 by 2 and 3 by 3 determinants. We want to talk about n by n determinants for a square matrix, for an n by n square matrix. Okay, so let A be the matrix. Remember, we can write matrices like this as well. Be an n by n matrix. Now we want to define what we mean by the determinant of this matrix. So the determinant of this matrix looks like this. Well, looks horrible, but there's another way to state it that makes it look easier. So let's look at it in this example. So we have a 4 by 4 matrix here. So we define something called A12, which is going to be a matrix, kind of a submatrix of this matrix. So remember, this always tells us the row, and this always tells us the column. So by A12 we mean we're referring to knocking out this row and knocking out this column. Okay, that's what we mean here. So if I knock out the top row and the second column, then I'm left with negative 2, 0, 5, 4, this, which is this. Okay? So that's what we mean by A12. So what we're going to say, the determinant of the whole thing is, we're going to start with this item, knock out this and this, then we're going to have this matrix. Then we're going to do another one where we're going to knock out, we're going to work with this item, knock out this, and so on. So let's see what happens. So the first one, we knock out this and this, so we let 1, 0, 5, so you can see this one here. Okay, the next one, we're going to knock out, we just did this last one, so that's this one, you're going to see that here. The next one, we're going to knock out the first row and it's A13. A13 is the first row and the third column, so we're going to have this, 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 which is here. Okay? And then we're going to do A14, that was A13, now we're going to do A14, which is this one, first row, fourth column, A14, knock out this, and you have these, which is here. Okay? So the determinant of this is going to be related to the determinant of these submatrices, these four submatrices. And the way it's going to be related is we're going to take the submatrix, this submatrix, multiplied by this item here, this was the A11 item, times that. The A12 item was here. This is the submatrix. We're going to take the 2 times that, this 2. Then this was the A13. So that was the A13 matrix. We're going to take this times that, which is the 1 here. And then the A14, this matrix here, which is here. And then the A14 element, which is here, Okay, so we're going to do all of that. And then the only other thing you have to do is worry about whether you're adding or subtracting. So here, -1 squared is adding. Here, -1 cubed is subtracting. Here, -1 to the 4th is adding. Here, -1 to the 5th is subtracting. And that is the formula. So that's what this says here. It says that the determinant, you take the A11 submatrix, find its determinant, the A12 matrix finds its determinant, and so on, all the way out to the last one, multiply by the corresponding element, the A11 element, the A12 element, and so on, and work with these minus signs and plus signs. So how did the minus sign and plus signs work? This is 1, 1, this is 1, 2, this is 1, n. So you can see where the exponents for the -1 come from as well. Okay, so that is the formula for the determinant of this A matrix. But, however, now we have these, this is the determinant of the, what is this called? The A11 matrix. This is the determinant of, this is the A12 matrix. So now we still have to figure out the determinants of these. So, do they do that? Well, I guess they do it. So we know how to do that already. So you can do that. Okay? So you can figure out where these numbers come from. Now what if this wasn't a 4 by 4, but this was a 5 by 5? You do the same kind of thing. If you had 5 columns and 5 rows, you'd still take, this would be the first one, and then you'd knock out this, and you'd get a 4 by 4 matrix. Here we see a 3 by 3, but you'd get a 4 by 4 matrix, and then this one, and you'd also get a 4 by 4 matrix, and so on. And then you'd have to do this again on the, because you'd be asking for, this would be the determinant of a 4 by 4 matrix, and you'd have to do all of that again for each one of these. So it's kind of a lot of stuff. I guess you could program a computer to do it, though, quickly. The determinant of the submatrix Aij is called the of A is called the ijth minor of A, and the quantity -1 I plus j of the ijth minor of A is called the ijth cofactor. Definition 6.5 is known as the cofactor expansion of the determinant along the first row, since the determinant of A is written as the sum of the products of each entry of the first row and the corresponding cofactor. It is natural to ask if one can compute determinants by cofactor expansion along other rows or other columns. Happily, the answer is yes, although we shall not prove this. So you don't have to use just this row. You could have used this row. So let's say you use this row. So that means you'd start with this one, and you'd get a matrix which would consist of 1, and then 7, and then 0, and 3. You'd knock out this whole row. Oh, I'm sorry, I made a mistake. Suppose you did this. You'd knock out this one and this one. So the minor would be this one. You don't include this one because this row was knocked out. This one, this one, this one, then this one. You don't include this because this row was knocked out. This one, so on. So you could do it that way, and then the next, you'd go to this element. That would mean you'd do this, 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 and this, and so on. Okay, or you could use any row, or you could use any column. Yeah, so you could use this column. So you do this is the first element, then this one, then this one. So if you're working with this one, you would knock out this row and this column, and then you get entries 2, 0, 2, 1, and so on. So you can do it along any row or any column. So the determinant of A can be computed by cofactor expansion along any row or column. So here we're taking the ith row and looking at all the elements in that row. Or here we're taking the jth column and looking at all the rows along that column. And then here they do some example of this using a 4x4 matrix. They do expand around the bottom row. So that means we're going to go here, then this element, then this element, and then this element to get the various cofactors. And that's going to be our cofactor expansion. And if you work it out, I guess you get this.